All right, sorry about that. Just realized that text didn't go through that I needed to settle. All right. So yeah, next problem. 2 commercial jets flying at 40,000 feet I'm guessing that is a red herring, or probably not necessary, are flying towards an airport. Okay, so that means that if we're thinking about this in this triangle, both of their sides are shrinking. So we're going to need to make sure we say that their rates of change are negative. Plane A, I guess I'll call this one A, just to kind of keep consistency with how I've been labeling things, and we'll call that plane B. 100 miles from the airport is flying south. Fine. If it's flying south, this has to be plane A because south is that way. I'm not going to redefine north, south, east, and west. So flying south at 520 miles per hour, while plane B flying, or 200, so this is currently 100 flying down at negative 520 miles per hour. And this is currently 240 flying west, so negative 450 miles per hour. How fast is the distance between the two planes changing at this time? So, which of these sides is not changing? None of them. So how fast is the distance between the two planes changing? So the distance between the two planes is that dotted line connecting them. That's going to be dc dt. So we want to know dc dt. So it looks pretty open and shut to me, because we know a squared plus b squared equals c squared, and when we take the derivative, we get 2a dA dt plus 2b dB dt is equal to 2c dc dt. Like, that's pretty straightforward. We've seen, 5 or 10 of these in the 10 problems that we've done in this class with these. We can divide them all by 2, so cancel out the 2's. And then if I look, I know that A is 100, A is negative 520. We know that B is 240, and that B is negative, or dB dt is negative 450. We know that C is, we don't know C. So we'll need to solve for C, we'll need to find that. And then we want to find dc dt. So if I want to find C, well, I know that we have 100, 240, and then we don't know. So the algebra 1 way to do this is to say 100 squared plus 240 squared is equal to C squared, and then we go through and we solve that. I don't have a calculator right now, so I'm going to scale this until it's numbers I can deal with. First, I'm going to divide them all by 10. Then I'm going to divide them all by 2 and get 5 and 12. And now, this is a right triangle that I know. It's a special right triangle, a 5, 12, 13. So to figure out what number that actually should be, I just undo that scaling down that I did. So the last thing I did was I divided by 2. So I'll undivide by 2 and I'll get to 26. And then I divided by 10, so I'll multiply by 10 and get 260. So that's 260. Now that we're here, I could say that my final answer is going to be negative 52000. I'm not figuring this number out. All that divided by 260, and that's going to be miles per hour. And that's going to be equal to dc dt. All right. So hopefully that was helpful, talking through that question. Let's look at our next one. So we skipped 19 and 20, and we're jumping straight to 21. So sand falls at a rate of 30 feet cubed per minute on top of a conical pile. Cone. Volume is equal to 1/3 pi r squared h. I don't even know what the question is. It's gonna be a volume question. The height of the cone is always 3/8 of the base diameter. Oh. Height is always gonna be 3/8 times the base diameter. Well, we know that instead of diameter, I could write 2 times radius, because diameter is equal to 2 times the radius of any circle or any circular object. So we'd say h is equal to 3 over 8 times 2r. So that's 6 over 8 or 3 over 4r. So we can say h is equal to 3 over 4r. Now, I don't know what I need to do yet, so I might need to alter some things. How fast is the height changing? Oh, they want me to find the height changing again. Okay. They could have asked us to find the radius changing. They're allowed to. So because of that, I need to eliminate r. So to do that, I'll multiply both sides by the reciprocal here, the 4/3. Still on camera? Okay. 4/3, 4/3. So we can say 4/3 h is equal to r. And so then we can say v is equal to 1/3 pi r squared. Nope. 4/3 h squared. H. Right, instead of writing r, we're writing 4/3 h. And then just gotta clean this up. So 4/3, that's gonna be, so 1/3 pi. 4/3 is gonna turn into 16/9 h squared h. So, and then 16 pi will be on top. And then 3 times 9 is 27 will be on the bottom, h cubed. So 16 pi over 27, 16 is a bunch of 2's multiplied together, 27 is a bunch of 3's multiplied together. So it's not going to simplify. It asks how fast is the height changing. So again, I shouldn't have started and done all this. I should have really read and seen what it's looking for. But how fast is the height changing? That's dh dt. When h is 2 feet. So if I take this derivative, I'll get dh dt is equal to 3 times 16 pi over 27 h squared dh dt. We'll just do what we normally do. You know, we can solve first or plug it in and solve first, but first I'm going to see that the 3 and the 27 are cancelled to 1 over 9, so it's going to be 16 pi over 9, and then 2 is going to get plugged in for h. And did I write dh dt? I should have written dv dt here. And dv dt is 30. So it says sand falls, but that sand is falling onto the conical pile, making it bigger. So it's a positive. So we'll multiply by the upside down of this fraction, so 9 over 16 pi. And then we'll divide it by 2 squared, which is 4. That'll be dh dt. Just make sure we put the appropriate units on it. So feet and minutes, so feet per minute. And sure, you can go through and find what number that is. What, 270 over 64, which certainly will simplify. Or 270 over 64 pi. You know, so what's that going to be? 185 over 32 pi feet per minute. All right, next one we see is 27. A spotlight is on the ground 21 feet away from the wall, and a 6-foot tall man is walking towards the wall. Why is he walking towards the, okay, at a rate of 2 feet per second, as shown in the video. So that's 2 right there. That's the man. How fast is the height of the shadow changing? Oh. So that's his shadow, right? And that's the actual man. How fast is the height of the shadow changing when the man is 6 feet from the wall? So we're going to need to, so for part A here, we're going to need to figure out a way to, oh, okay, and we know that this is 21. All right. So we're trying to relate, oh, the man is always 6, right? So, And, so we know that there's this lit up area, and then this is all like shadow. And so we need to figure out how to relate. Let's see, how fast is the height of the shadow changing? So we want ds dt, right? If I called this s, I might have to change the variable name in a minute. So this is like getting longer. This is getting shorter. But this is 21 the whole time. So there's really a couple of things going on here. But I feel like at any given time we have a set of right angles here, meaning we have a set of similar triangles, because whatever the angle is between the light and the man's head is the same as the angle between the light and the shadow's head. So they've got angle, side, angle. Wait, isn't that congruency? Oh, right. They have angle, angle, similarity. That's what it is, because the sides are different lengths. So, like, we don't know how long this thing is here. We know that this is 6. We don't know how long this... No, we do know how long this total side is. And we know that that is... We're not quite sure. So we could almost be like... If we're dealing with the little versus the big... So in the little triangle, we know the man is 6. In the big triangle, we know it's the shadow length. That's my cursive S, so it doesn't look like a 5. I guess that kind of looks like an 8. Shut up. All right, let's try again. Quit being right. Nobody said it but you. Stop it. All right, so there's S. Okay, 6 over S. We'll call this S right here. Right? That shadow length is growing. If you're wondering why I've paused so much, it's because I'm really trying to figure this out. And I'm a little slow at these. So 6 and the shadow, and that's going to make the distance he is from the light source. So you call that, what, L? Distance he is to the light source is the little triangle, and the big triangle is going to be 21. So how fast is the height of the shadow changing when the man is 6 feet from the wall? Well, all we would need to do here, we want to find the height of the shadow changing. Well, let's see. Couldn't we just take the derivative of this? Now, so the calculus is tricky on this one if we were to do that. But we could. This is really annoying me calling it L like that. Let me use a capital L. So shadow and L. So if I like cross multiply here, 6 times 21 is what, 126? And then we're going to have S, L. The problem is if I take this derivative, we'll get 0 is equal to ds dt L plus S dl dt. It's true, and I think we could calculate everything we need, couldn't we? So ds dt is what we're looking for. L, man is 6 feet from the wall. So if the man is 6 feet from the wall, that means that how far is he from the spotlight, the way that I set it up. If he's 6 feet from the wall, that means he's 15 feet from the spotlight. So we say 15 ds dt plus S. So then what would the height of the shadow be then? Well, that's going to be 6 over height of the shadow is equal to 6 over 21. Wait. Really? So the shadow's 21? And then the LDT, we know that that's 2. So then that equals 0. Oh dear. Cool. I might have to make a cut in this video. So I get negative 42. Oh, wait, no, okay, I'm okay with this. So 21 times 2, I get 42. Subtract from both sides. Then I'll divide it by 15. 42 over 15 is going to be ds dt. And that's going to be feet per second. And I got confused because I was like, wait, that means the shadow is getting smaller. But think about it. If you've got a light here and someone's walking away from the light, that shadow, as you get farther and farther away from the light, gets lower and lower and lower on the wall. So I'm going to go double check really quick. Okay, so I caught my error. I made a baby mistake. It's not a mistake in the ideas. It's a mistake in my... Here, I'm going to go back to here. So I said earlier, the man is 6 feet away from the wall. So if the man's here, he's 6 feet away from the wall. We said he was 15 feet away from the light source then. So I was supposed to say L is 15, not L is 6. So I should say L is 15. That means when I solve for S, I'll get 15S is equal to 6 times 21, which is 126. So S is 126 over 15. Much yuckier number. So then over here, S isn't 21. S is 126 over 15. 126 over 15. So instead of getting a nice ugly fraction, I get a slightly uglier fraction. So now we'll subtract the, what is that, 252? Let's leave it times 2, why not? So we'll subtract it from both sides. We'll get negative 126 over 15 times 2. Then we'll divide that by 15. We'll get some number. It's approximately negative 1.120 feet per second. Okay. Have S is the angle of elevation changing at that time. So what we could do then is we could, angle of elevation is going to be the angle between this and the guy's head, or this and the top of the shadow. Doesn't really matter. Do some trig. Oh, I only have one more to do after this, so I have time to do that. So angle of elevation, that angle, doesn't matter. Since I called this right here L, I really should stick with that. So then I can use, so if I call this L, I call this theta, call this 6. We all know dl dt is 2. So I can say that, that's tangent. Oh, so tangent theta is equal to 6 over L. Ooh, this one's not going to be as good because 6 over L, that derivative is going to be a little bit more annoying. That's worth talking about. So when I take this derivative on the left-hand side, we'll get secant squared theta d theta dt. And on the right-hand side, since it's 6 over L, I just want to remind you really quick that that is 6 times L to the negative 1. So when we take this derivative, the negative 1 is going to pop out front. We get negative 6L to the negative 2 dl dt. So I'll call that negative 6 over L squared dl dt, right? Because the negative 2 flips it down to the bottom. And now we're looking for the change in the angle at that instant. So at that instant, so we're going to have to find what theta is. Thankfully, we know that theta is this, that's 6, and L we said was 15. So if I wanted to find this, I just do inverse tangent of 6 over 15, and I get come on, computer, trig, inverse tangent. Inverse tangent. 6/15. Let's see. Inverse tangent. It's in degrees. Cool. 21.8 degrees. 801, sorry. 801 degrees. 21.801 degrees. All right. So, then a secant of that squared I got a really tiny number. I got like 0.000344. I'll divide both sides by that. Regardless, he gets negative 0.046 radians per second, or negative 2.634 degrees per second. So, yeah, should work out. On to the last question. I'm running a little bit out of gas here. A little bit more out of time. All right, let's see. Oh, unintentional joke. Okay. An analog clock has a 4-inch minute hand and a 3-inch hour hand. How fast is the distance between the tips of the hands changing at 4 p.m.? Well, let's see. At any given time, we could say the distance between the tips of the hands. Oh, wait, this is just a right triangle then, isn't it? Honestly, we're going to have to do like arc length or something, but fudge. Ladies and gentlemen, I told you we're not going to do non-right triangle stuff. This is another example of the law of cosines. I didn't look closely enough. I thought this was going to be talking about the time, the length of the arc around the outside of the clock. Well, I guess instead of me going through and doing the law of cosines on this, I'm just going to have to call it a day. Hope this was helpful. Canfield out.